we have something new here. Oh, what is this? Iowa. Cassette tape player. Not this one. Here. This is my previous project. This is a dimmer switch. This is the circuit diagram. 12 volt supply, and then we have the resistor in series with the LED, and then we have in series with the potentiometer to the ground. And we have here my layout. What seems to be the problem here with my old design? It is not fully turned off. So I decided to make a new circuit. And now we have here our new module. This is a dimmer switch using a transistor. We are now going to see the design of the circuit. And we have here, I'm using a 12 volts power supply. The base is connected to the, not this one, to the middle. That's the initial. Or let us say, let us first set this potentiometer. I'm setting the potentiometer into the 0 ohms range. 0 ohms. And then the base is now here, the emitter to the ground, and in the emitter is in parallel our output LED, and this transistor 2N3904, the collector, it has no resistor. That is my design. And this one is the power LED. As you have seen here, what type of transistor configuration we have. What do you think is the type of transistor configuration? This is a transistor common collector configuration, better known as emitter follower. If this is a common collector, it seems that the collector is not common. How did you say that this is a common collector configuration? Well, in this configuration, you can use common collector configuration or terms when you are analyzing this type of circuit and using this circuit as an amplifier. So the common collector terms is only used for this type of circuit while you are using this as an amplifier. Emitter follower is for DC biasing or for using this circuit as a switch. So this transistor, we're now using this as a switch. Let us now see the operation of the circuit. If this is an emitter follower, what makes this an emitter follower? At the initial state, when you power on the circuit and you set the potentiometer to 0 ohms, current flows into this way, to the base, to the emitter, to the collector, to the emitter, and to the emitter and to the load. powering on the transistor, and the load is turning on, and we got this power LED. It means the transistor here is saturated because there is a current that flows into the base, forward biasing the transistor. While this type of circuit is we're going to compute the value of all the resistors. There's a first KBL here, BCC RD2D2. This is the first KBL for computing the values of RD2, power LED, BCC RD2D2. So we got here the KBL, 12 volts minus the 2 volts, voltage rating of this LED given in the data sheet. We got 10 volts voltage drop at RD2 using Ohm's law. Transposition, substitution, current rating of the LED 0.02 given in the data sheet. We got 500 ohms, and I'm using 1 kilo ohm, my available resistor, and it's okay. So we got the first value of RD2, 1 kilo ohms. Now we got this, a second KBL. Current flows into the BCC, to the base, into the emitter. In this circuit configuration, it seems it is complicated because we're taking the output at the emitter side, and the output load is in parallel with the emitter resistor. What is this? We're going to compute for the voltage input. What is the voltage input? Let us see this figure. Figure 2, diode equivalent circuit of transistor. Okay. We have the first KBL here up to the point E. When setting the potentiometer to 0 ohms, current flows to the 0 ohms potentiometer, and then the base resistor, and to the base to the emitter junction of the transistor. That is equivalent to voltage input. Voltage here at the node X to voltage at the node E. That is voltage input. We computed that voltage input to turn on this transistor. And let us see now the computation. So, as you have seen here, in an emitter follower, it should be the voltage input is equal to the voltage output. Voltage output is taken into the emitter side, and the voltage input is from this node XE. So it consumes a large resistance value before it becomes a supply to the load. So this one, it should be 12 volts minus the voltage drop at the R1, RB, and the base to emitter junction of the transistor, and whatever the voltage there is now the input voltage for the load. By computing that, BCC 0 ohms plus the voltage drop RB, voltage drop BE, we got here. And then we know the BCC or the BCC. That should be BCC. So, voltage drop now is 11.35 volts. So Supposedly, we're having this 12 volt supply. But because to compute first for the voltage input, it passes to different resistance. So it consumes a lot of impedance or resistance. It makes this our voltage input 11.35 volts. So passing to this node, into this node, turning on the transistor, it will make this as a voltage supply to our load 11.35 volts. It consumes 0.65 volts. And in here, whatever the voltage drop at the base is now the voltage input. We calculated it to this node. Here, X to E. Because this is the load. We're not included the load yet. The voltage input first, which is the sum of the VCC minus the voltage drop of this circuit or this line makes this 11.35 volts. It consumes 0.65 volts just to make a voltage input for the load. This is just voltage input. And this makes emitter follower a high impedance circuit because it consumes a lot of resistance to make it a voltage input. This voltage at the RB is now our voltage input to the load. Remember, this is the load. So in here, using Ohm's law, we get RB is, what is this? 1 milliamp. 11,350 ohms. Okay, 11,000 kilo ohms available. Okay, where did we get this 1 milliampere? In my circuit, I set a value of 1 milliampere to the base. That is my design. I'm setting the base current here of 1 milliampere because I know in the data sheet of this transistor, it is capable of switching up to 100 milliampere. If this is collector current is 100 milliampere and our base current is around 1 milliampere and the current gain is 100, it will make 100 milliampere to flow into the collector of this transistor. That's why I set the value of 1 milliampere as a base resistance due to the current gain formula or behavior of the transistor. And we are now having this. I'm using 11 kilo ohms for the value of RB. Why did I just compute the output side in reference with the output side 100 milliamps, the capabilities or the capacity of the transistor 2 and 3904 as a switch 100 milliamps according to the data sheet. Let us now consider this figure, equivalent circuit showing high impedance. So as you have seen here, this is now our load. This is now the input voltage. And we computed that 11.35 volts. That is appearing into the base resistor. This is now our voltage input, having a current, that is a current of the base 1 milliamps, and 11.35, this is now the voltage source of the load. This voltage input 11.35, not 12 volts. This 11.35 now is the new voltage supply to the load, and 11 kilo ohms. Did you see this? That makes the circuit a high impedance input. Okay. This makes emitter follower a high impedance circuit because it consumes 11 kilo ohms as an input resistance. Okay, consider this figure 3-point equivalent circuit as if we are just like having a voltage supply of 1135 volts. We're going to supply that into the emitter resistor. See? 11.35, 0.65 is being consumed by the internal circuitry before it becomes about voltage supply of this emitter resistor. Just like this one. We're now having a new supply, 11.35 volts. And then, okay, because of that, we're now going to compute for the Kirchhoff's voltage law. Voltage input minus the voltage output. Voltage output is the voltage in the resistor emitter, which is also equal to the voltage output, voltage RE. Voltage input minus voltage output is equal to 0. That is the KVL. Using that transposition, and we got 1135 volts. So in emitter follower, voltage output is equal to voltage input. Makes this a okay. Therefore, voltage input is equal to voltage output in case we have this emitter follower circuit. And let's go back now here. Since the voltage input is equal to the voltage output is equal to the voltage appearing into the resistor emitter. Okay, so all the same, 11.35 volts. Let us now come to the next figure. Still, we're setting the potentiometer into 0 ohms. That's why this transistor is conducting and it's supplying current to the load. Circuit diagram R1 set to 0 ohms. Okay, let us now see this. This is now the explanation. Where did we get that? This collector emitter at saturation. Since we are setting the base current of 1 milliampere using the current gain formula, IC over IB. IC, collector current, is equal to the collector emitter at saturation of this transistor. Since it's just we're using the transistor as a switch in saturation mode. IC is equal to the collector emitter at saturation of this transistor. And the base current, HIP, is equal to IC over IB, happens to be the current that flows into the RB. That is the base current, current IRB. By transposition, and I'm using HIP of 100, or also known as beta. Substitution, transposition, okay, transposition. IC is that now is, since we know that the base current 1 milliamps, we're setting the base current to 1 milliamps and then 100, the HIP. We get now here 0.001 ampere. or 0.1 ampere times 100 or 0.1 ampere or 100 milliampere. That is now the collector resistor collector current or the collector to emitter saturation current that flows into the collector emitter, also equal to the collector current. We have no resistor here in our design. We are using current multiplier function of the transistor. So we're using the current multiplier as a current driven device with this, setting the current of the base to compute for the IC. Okay, that is the KBL at node E. Whoa, we have a KBL at node E here. IC is equal to current at RE plus current I1. Where is that? So in here, IC, which is the total current, which is 100 milliamps, because this part is just a voltage input or the current input of the device. We are using a current here because this is a current driven device. IC, which is the total current, is equal to the current now is dividing. So it means when we have a load here, we have a load of a LED which have a current of I1 and a current of IRE to the emitter. The current in parallel or using this, since I1 is equal to ID1 is equal to RD1 0.02 20 milliampere. We know the value of the load current here given in the datasheet of the LED. As if you're buying a device or equipment, always the load current is given, and this is given 20 milliampere. The current I1 is 20 milliampere, and the current total, the supply current now is the IC or the collector emitter at saturation, which is 100 milliamps. Therefore now IC is IRE plus I1. Okay, there's a current division here at the emitter side, RE and into the load. IC SAT. Okay, we know the value of the supply current and the load current. We got now the value of resistor to emitter of 80 milliampere. So the current that flows into the emitter resistor is 80 milliampere. When we have a load, 80 milliampere here and 20 milliampere here, because we are supplying a 100 milliamps. We have the supply of 100 milliamps. Ohm's law, since we know the voltage drop here at the RE, which is equal to voltage input, voltage output, 11.35 volts divided by 0.08 ampere, also equal to 80 milliampere. So I got now 141.875 ohms calculated. I use 100 ohms for my emitter current. That is now with the load. I'm using 100 ohms. Since we know that voltage output is equal to the voltage at RE, okay, 11, also equal to the voltage output. Okay, therefore voltage output is equal to voltage drop at RD1 plus voltage D1. Since they are in parallel, voltage in parallel is equal, it means this voltage output is equal to the voltage drop of RD1 plus the voltage drop at D1. Because they are in series, voltage in series, voltage drop at RD1 in series with the voltage drop at D1. So the sum of the two voltages makes this an output voltage. See this? Okay, I also use you can use a KBL method. Voltage output is now the supply voltage minus the voltage at the RD1 minus the voltage at D1 is equal to 0. That's another technique. Finding the voltage of at RD1, voltage output minus the voltage of the LED, which is 2 volts given in the datasheet. We got now this voltage drop at RD1 of 9.35 volts. Since I1 is equal to RD1, ID1 20 milliampere. Okay, we know that the current in series is equal. Whatever the current ID1 is equal to the current ID1. This makes circuit a low output impedance. Did you see that? The output impedance is very low. We are just using 100 ohms here for the emitter. That makes the circuit a low impedance output and high impedance input. Using Ohm's law, since we know that RD1 9.35 volts from the previous computation, and then the current rating of the LED 0.62 ampere. Since they are in series, whatever the current that flows into this resistor is equal to the LED. We got now this 467.5 ohms by using 470 ohms available. Now we have now here setting R1 into maximum, not maximum, just 125 kilo ohms into the middle. When you turn on the knob, this one, when you turn it, setting it to maximum, it will make the LED to turn off. What make this happen to the circuit? Why is it turning off? Let us now check. When you're turning the knob, increasing the resistance, makes the current to flow. There's no flow of current here. This makes the transistor in cut off. Once you fully reach the maximum, once you increasing the resistance, you're increasing the resistance little by little, it will decreasing the brightness of the LED until you reach the 125 kilo ohms. That makes this transistor to operate in cut-off. Almost there's no current to flow. When there's no current flow here into the base, there is no collector current flow in the output side. There's no collector current output side. There is no supply current to the load. So there is no supply current to the load. There is no light to the LED. Okay, let us now see this. We have now, by computing now the voltage input, VCC is equal to voltage at the Y to the E. Voltage input is equal to voltage drop at R1. Did you see that? That is R1. I'm setting this to maximum 125 kilo ohms. There is now a voltage drop at the R1, RB, and to the base to emitter junction of the transistor equals the voltage input. This is a voltage input. And because of that, we get now the two values of voltage drop here, the sum of the two values by computation. And we know that base emitter at saturation of the transistor 0.65 volts. Given datasheet. Transposition, calculation, simplification, 11.35 volts. The sum of the voltage drop at R1, RB1. When we increasing the resistance here, current will not flow into the collector. It is cut off because too much resistance here. Okay, let us now see here. We derive this equation 11.35 BR1 plus BRB. In terms of IR from Ohm's law, since the base current here RB is equal to the base current R1, they are in series of this settings. R1 is in 125 kilo ohms range. Substitution, substitution IB, same base current since they are in series. We got now this, simplifying, we got the base current of 0.0000825 ampere. That is now our base current. We need at least, what is this? It means it has 83 microampere or 0.0000835 ampere. 83 microampere, very small. This is now the proper. Setting this into 125 kilo ohms. Okay, this will make the transistor to cut off. Not totally cut off. There's still a current that flows, but the problem is that current that flows into the collector current is not enough to drive the load. You can see that there is a base current 0.000835, and when you're using the current gain formula for that, for computing the collector current IB substitution, we got 0.00835 ampere. That is now the supply current being to be delivered or being to be supplied to the load, which is not enough to drive the LED, because if this is the current supply to the load 0.008, but the LED is to turn on 0.02 ampere. This is only 0.00835 ohms. That is not enough to turn on the LED, but still there is a current flow here, very small, but that is enough to turn on the LED. That's why this LED is turning off once you increasing the value of the base resistor, making this not totally cut off, making the current to flow at the collector very small because of the resistance of the base. You see here KCL at node E, IC sat, now the supply current is equal to, and then if your current is 0.00835 ampere, and then you're going to supply it into the resistor emitter and to the load, you got this negative at the resistance of the emitter. You don't have, what is this negative current? There's no negative current. Negative means is used only for computation. If this is negative, the current direction is not correct, so there's no negative current in the real world, because our arrow here is pointing downwards to the ground, not upward. That's the assignment of the current law. That is the based on mathematics computation of a circuit. If you put the arrow upward, this is okay, but we're assigning the current to flow into the ground, and we got negative, so there's no negative current. Besides, we're supplying 0.008 or 8 milliampere. 8 milliampere is being supplied to the load, to the emitter resistor and to the loads. This emitter resistor is some sort of a buffering resistor for the load. You need this. So this will never turn on the LED. It needs 0.02 ampere or 20 milliampere. But our supply is 80 milliohms. 80 milliohms. Not the supply. The supply is 80 milliohms. Okay, 80 milliohms. So we got now here our schematic diagram for the dimmer switch. I'm using the jumper settings. If I'm going to use the onboard, this one. If I take away the jumper settings, the onboard it will be disconnected, and we are now going to use the other output pins for the external. If you're going to use the external and the outboard, it's still okay. The combination of the two connection. This is now my layout. That is the operation of the circuit with this emitter follower configuration. Okay? Thank you for watching the video.